Yep. The final is a standardized ACS test that covers the whole year. I may actually have a little bit of a supplemental, but it'll mostly be this ACS test. There are study guides for this ACS test available. You can talk to Dr. Anderson. She'll probably put you in contact with the people. I think our Chem Club sells them. Okay. Um, I think there are, I don't know what they cost exactly. So you'll have to look at that. I think it's upwards of, it's $30 or $40 or something. So they're not cheap. Um, Dr. Anderson did buy a number of them and put them in the library under our names. So what you can do is go to the library. It's probably one of those, you can check it out for an hour or two in the library. So somebody doesn't take it home and then nobody will see it ever again. I also have, I'm looking at my shelves. I had 2 old copies on my shelves, and chemistry doesn't change. So the first 2 people to come to office hours and ask for one, I'll just loan it out to. Okay, so my office hours are 1:15 to 3:15 today. Um, and tomorrow I have office hour. I can have office hours by appointment between 10 and 2:30, but you'll have to let me know, and you have to let me know before tomorrow morning. Okay, I have somebody already coming in at 10:30 for that. And then there'll be a quiz on Friday as usual, and then you'll have a homework due on Wednesday. Questions on things we're doing? I finished grading your tests. I also have your quizzes. Remind me to stop at 5 minutes before the end of class if I don't remember on my own. And if there aren't questions, there are other questions. All right. I saw some big eyes about a final that covers both terms. Just this is what happens in our chem classes. It's going to be curved, so it's based on, there are national norms for these, just like there are for like your you take what, ACT or SAT maybe. I think people have taken that less, but it gets curved, it gets the national norms, and then I'll curve it on top of that. Sandra, do you still have a question? Nope. All right, then what we're going to talk about today is we're going to talk about free energy more, right? We have our equation for free energy, and we're going to continue to do a bunch with it. We may modify it a little bit, but remember our equation is that the free energy, remember this is the thing that tells us whether a reaction is spontaneous or not. And when we talk about a reaction being spontaneous, we talk about, let's say this is our reaction here, that's a D. If the reaction goes this way, that's spontaneous. Okay, and our delta G is less than 0, meaning it's negative. Okay, if a reaction instead goes this way, that's non-spontaneous. Okay, and our delta G is going to be greater than 0. Okay, or positive. So we talk about spontaneity, that's what we mean. And then if a reaction, right now these are standard conditions. So they're going to tell us whether the reaction is favored in this direction or that direction. But we're going to actually talk about non-standard conditions like in 5 minutes or less. And when delta G is 0, which it can be for non-standard conditions, it can be for standard conditions too, but you'll never see it. When the actual delta G is 0, that means you're at equilibrium. You're not going this way or that way yet. Questions? Okay. So delta G is going to be equal to our free energy is going to be equal to our standard enthalpy plus, minus our temperature in Kelvin times our standard entropy. So let's name these things. Enthalpy. The little circle means standard, okay? And we'll talk about that more in a second. This is free energy. It's officially Gibbs free energy, but we really just talk about it as free energy. This is entropy, okay? And this is going to be our temperature in what? Kelvin, right? Okay. Questions? All right, then let's talk about what standard conditions are. So I was reading in your book and I was surprised that they were different than what I was taught. It may be that they've evolved. So I'll talk about that really quick. But standard conditions. All right, so standard conditions are a pressure. It's 1 atmosphere pressure of everything, okay? And it's actually, if it's in concentrations, it's molality. Remember, molality is moles over kilograms, okay? So that, but usually we're not working in those. Usually we're working with solutions, right? And there aren't pressures in solutions. And so they generally talk about and usually we think about 1 atmosphere, okay? Actually, I said 1 atmosphere everything. I meant 1 bar. A bar is almost the same as an atmosphere. It's like 1% difference. But so for chemistry, what we do is we just say, I think this is probably historical, we do 1 atmosphere instead of 1 bar, and 1 molar everything. Because we usually work with molar solutions, not molal solutions. If you grow up to be a chemical engineer, they'll probably work with molal a lot because they care whether something's off by 1% or something like that. So that's the conditions. There is no standard temperature. All right, but often things get written in the tables we're seeing in this book are at 298 or 25 degrees Celsius, so 298 Kelvin. But there's no standard temperature according to our book, which is maybe why I've always been confused about whether it was 0 or 25 degrees Celsius my whole life. I think maybe these things have evolved, but we're going to follow the book for this. Okay. So what we need to do though is we need a way of figuring out. So the biggest thing here, we've got a temperature that'll move things around. But the biggest thing is, you've done a bunch of stuff in the lab. Last lab, did you have concentrations of things? Yes? Were they 1 molar everything? No. How about the lab before that? Yes. Yes, they were? No. Okay. They probably were never 1 molar everything, right? Standard conditions assumes you've got 1 molar of products and reactants, and probably you just start with reactants, right? And they're probably not 1 molar anyway. So we need to be able to look at these things under conditions, or whether a reaction is going to be spontaneous under conditions where it's not 1 molar everything. And so we need a correction term for that. And so if we look at this, we have, the way this goes is the free energy. Notice I didn't do a little standard thing next to it. I guess that can be a different temperature, it can be different concentrations. The free energy is going to be equal to it's going to be equal to the standard free energy plus a correction term, which is the ideal gas constant times the temperature times the logarithm of QP. So this is the reaction quotient, but with pressures. All right, so let's go ahead and quickly label these out. So this is the ideal gas constant, and it's the form that has joules in it. So, I mean, you could use any value, but then you'd have to use other things as well. This is the temperature in Kelvin as usual. The free energy with the little circle next to it is the standard free energy. So it's the one where everything is at 1 molar everything. And I'm going to call this just free energy, I'm often going to say, or I might say real free energy, or I might say actual free energy. Okay, actual free energy is a term I made up. All right, it's probably just free energy, but I want to emphasize that. This is the reaction quotient. All right, before we start using this, I want to talk about this QP thing. I was looking at this last night and I was thinking, I don't even remember learning QP, but they probably talked about it, okay? Because as a chemist, you don't really use QP. You don't do things in pressures mostly. Some chemists do, but most chemists are doing things in solutions or using concentrations, not pressures, right? But they aren't equivalent. So QP is equivalent to QC if no change in gas molecules occurs. Okay, no change in, let's say, number of gas molecules occurs. So what do I mean by that? Well, let's say I have the reaction here where I have, we've got hydrogen gas reacting with oxygen gas to make water gas. I'm not going to actually, water gas is its own thing, but it's water, that's a vapor, let's say. So I've got that. I'm just making this up off the top of my head, so we can just do 1/2 to balance that, right? And so over here on this side, I have 1.5 molecules of gas, and I have 1 molecule of gas, right? So for this reaction, if I was trying to do it with concentrations instead, this is QC is concentrations, QP is not equal to QC. All right, yes?
For the equation that you gave us, like the free energy equation,
Mhm.
that's strictly for gases, right? Like we're not doing separate solutions with that.
We are going to, but I'm pointing out this place where it's different. And I'm going to show you how to do the conversion. And I'll probably give you 1 problem on the homework with it. And I will not give you a quiz problem. I will not give you a test problem on it because this almost never comes up when you're a chemist doing things in solutions. Okay. So you're probably okay, but I want you to be aware that it's there. If you go on to have a career in chemistry, you need to know it's there so that if you end up wandering through your research or your life path, you wander into where it's important, you know that you need to adjust. Okay, so if I had this situation and I wanted to work in concentrations, the way these two things are related is QP is equal to QC. And we saw this before the class when we were talking about equilibrium constants times raised to the number of moles. So if we take the difference in number of moles, all these other things we've defined at this point, except this is the difference in moles of, in terms of the written balanced equation of gas between reactants and products. Okay. Questions on that real quick? Like I said, I'm going to put a problem on your homework to emphasize it that much, and then I will not quiz or test you on something where it's QC is not equal to QP, okay? Because it doesn't come up enough. All right, so I'm going to rewrite my equation then down here, and we're going to say the entropy change, or I'm sorry, the free energy change is equal to the standard free energy change plus RT ln of QC. Okay, QC is the reaction quotient. I guess I could have led with that. Let's say it looks like that. Okay, and these are all things in solution, we'll say, so QC is equal to that. And so for this, that's going to be C, products of reactants. C has a 2 in front, so what do I do with that 2? Becomes an exponent, times D over A times B. Okay? This is like your equilibrium constant, right? Except this can be for any ratios. Or actually, maybe I should do it like this. These can be any ratios. Okay, if it was an equilibrium constant, it would be only for the ratios at equilibrium, but this can be any ratios of reactants and products along the whole reaction path. Does that make sense? All right, so we've got this thing, so we can convert, we can see what happens at equilibrium now, or we can convert between, figure out for an actual reaction. And this is important for anything you've done in lab because everything wasn't 1 molar. It's also super important if you work in biological systems because in biological systems, nothing is 1 molar. It's way too concentrated, okay? Your stomach acid is about 0.1 molar, okay? You've got about 0.15 molar sodium chloride in your blood, okay? But that's kind of the higher ends of concentrations you will see in a biological system. And most things are much less concentrated. All right, so we've got this, we've got the equation. Why don't we go ahead and work a problem? This is a good one right here. I'm going to pull it up. There's our equation. And what I'd like you to do is go ahead and work this problem. Okay, I'm going to remind you that our ideal gas constant that we're going to use is the 1 joules. It's going to be 8.314 joules per mole times Kelvin. And what are what's our delta G in? And what's our Rn? Joules. So you're going to have to, but they're both here, so you're going to have to make your units match. You can make your units match by converting joules to kilojoules or joules or kilojoules to joules. It's up to you. Okay, go ahead and work that. I'll give you, we'll go 2 or 3 minutes there. Please call me when you have questions. Pass some back things here to stay off the board.
What is this? HP. Are they both 0.030?
Yes.
Or
That's what
they both are.
they are.
Okay. Sorry, thank you.
Great. We'll go about a minute more here. See people are, thank you all for diligently working on it.
Is that one?
Okay, let's go ahead and work this one then. So using the data below, we need to calculate that. Looking at this reaction, how many moles of gas are there in the reactants? 0. There's no gas, right? None of these things are gases. How many in the products? 0. So even these are, and they're actually the same number of reactants and products. But even if there was even if I changed your reaction and I did this, right? Let's say that was the balanced formula. Even though there are more reactants and products, they're not gas. So QC is equal to QP. Okay, so we don't need to worry about the difference between QC and QP or do any kind of conversion there. So the first thing is we want to calculate what our QC is. Okay, and so that's going to be products over reactants. I'm not going to write out the general form. I'm just going to write the concentrations up here. So these are my products right here. So QC is going to be equal to 0.35. These brackets mean molar. Okay, and when you do one of these, there are sometimes, if you have the same number of products versus reactants, you don't have to convert to molar as long as they're all in the same units. Okay, if that didn't instantly make sense, or if you don't think about that, go, okay, I got it. Just always convert to molar and you will be safe. Okay, if you always convert to molar, you'll be safe here. And there are sometimes you don't need to worry about it. 0.58 molar. Once again, I'm going to not be redundant, and I'm just going to do the brackets there. And then my reactants are both at 0.030 molar. Like that. All right. If I remember from last hour, is it 225? Okay. All right. So that's what our QC is. So now we can go ahead and load that. That was one of our answers, right? These things are, all the units would cancel here, but these things are dimensionless anyway. Remember, our equilibrium constants do not have units on them. And so now we can actually calculate the free energy. That's going to be equal to the standard free energy plus our correction term. Yes?
It's 226.
Is it 226? Okay, great. 226. Okay. So our free energy change, I need it. This is in kilojoules, this is in joules. I'm just going to do this in my head, but remember, if you can't do it, if you make mistakes doing it in your head, always use dimensional analysis. That'll tell you what goes on, whether you multiply or divide. Okay, so this actually is the same as 59,100 joules. And then that's going to be plus, R is 8.314 joules per mole Kelvin. This is really joules per mole. Okay, times the temperature, which is going to be 298 Kelvin. Okay, times the natural logarithm of 226. And so then I can put this in my calculator. But before I do, spontaneous or not spontaneous? Not spontaneous, right? Because it's very positive. That's a huge, you don't have a feeling for this, but that's huge not positive number, really. At least from my sense is always biochemical, which is more, things don't get that positive or negative, really. Do I have more products or reactants here? Okay, so looking at the concentrations. More products, right? Well, the standard conditions are 1 molar everything, but now I have less reactants, right, than products. So it's going to make it even, what? Even more positive, even more non-spontaneous is what I expect. Let's see what happens. So if I put 226 in, take a natural logarithm times 298 times 8.314 plus 59,100, I get 70. We've got two significant figures in our concentrations, so I'm just going to use that. And that's going to be equal to 73,000 joules per mole. Is that what other people got, roughly? Remember, for significant figures, you just have to be within 3 as long as you didn't use 1 when it wasn't 1, okay? And I would always just give 2. If I think it's 1, I would just give 2 because I only have to be within 3. So then you're always safe. Questions? Okay, so this is really important. It's really important probably from all perspectives. I see it from a biological perspective because I've got all these standard free energies. If I'm thinking about glycolysis, I've got all these standard free energies that are in there. But none of those reactions in glycolysis are actually happening at 1 molar everything. All right, so I need to correct for those to figure out what the real free energy would be in a cell. Questions? Okay. Then I planned this lecture in a different order than I decided to give it. What we're going to do now is we're going to talk about how we can calculate free energies from one reaction from free energies of other reactions. So what I want to point out to you is, it's kind of slightly a change in topic. We have this equation, right, that says the standard free energy is equal to the standard enthalpy minus the temperature times the standard entropy. And what I want to remind you here is that, remember, entropy is a state function? What's a state function again? Something that's independent of the path. It just matters what the start and end is, okay? So entropy is a state function. Temperature is also a state function, right? Enthalpy is a state function. So what that means is free energy has to be a state function because everything that goes into it is a state function. So what that means is we can calculate the free energy change for a reaction based on adding up other reactions. So the free energy change for a reaction can be calculated from summing up other reactions. Meaning you're using a bunch of different other reactions to get from the same reactants to the same products. Does that make sense? Now we have this thing called standard free energies. So this is a table. We get standard free energies of formation. All right, so G delta F means standard free energy of formation. And what that means is that is the free energy to make something from its reactant, from its elements. So you take the elements and you make something. So what I can do is if I'm thinking about methane, which is natural gas, it's what comes out of your stove, it comes out of your Bunsen burner, and it burns. If I want to think about natural gas, the standard free energy for formation of natural gas is this. This is the reaction that's used. Whoops, there's no oxygen in that. Okay, so if I take a carbon and combine it with elemental carbon, I take elemental hydrogen, I combine them, I get methane, all right? And the standard free energies of the elements are assumed to be 0. You start there, okay? It's all relative sort of stuff. And so if I have a more complex reaction, I can add all the formations up and I can do the products minus reactants thing for those energies, and I can get the new energy for that reaction. I'm not going to do an example where I add up a bunch of these and write out the whole reaction, but the elements end up canceling. Okay, is what happens if you do this. If you were to add all those reactions. But I do have a reaction for us to do here. I think it was methane burning. Yes, it was. I was trying to get a more fun reaction last night. I just couldn't get anything that worked the way I wanted.
So is it the same idea that, the delta G reaction is gonna be the sum of the products times the moles minus the sum of the reactants times moles?
Yeah, so the question is this the same thing we did with entropy? Does that make sense? So it's products minus reactants. Okay, so this is if you burn that methane that comes out, makes the flame, right, out of your Bunsen burner or on your stove, we can calculate the free energy for this reaction by that standard free energy of reaction is going to be equal to the sum of the standard free energies of the products of this formation minus the standard free energies of formation for the reactants. Okay? I'm going to scroll down here so I have a little more room. Why don't you go ahead and try to do that? Can I make the table bigger? Okay. I can. I'm going to like run over my equations over here, but. So why don't you try that? I'll let you guys go for a little bit with it, and then I'll shrink it. But you're using these. And what I want to remind you is we've got the number of moles in front of each. So when you do water, gas, right, there are 2 of those. And so you multiply that number times 2. Yes?
I don't think there's been two. Yeah, oxygen.
There isn't, oxygen isn't up there. So let's add it. Oxygen, gas, it's the element, right? What's the standard free energy for it? A formation. What's it cost to make oxygen, the elemental oxygen from itself? 0. Okay, and it's 0 here too. You see how we have zeros for the elemental forms here, for hydrogen, for chlorine gas, for carbon? Does that make sense? Do note that for the entropies, it's not 0, right? Because we're not getting those entropy. We're getting those entropies at 298 Kelvin, not at absolute 0.
No, you're good.
I can't make it bigger without running off the screen. I guess maybe we don't need all of them.
My eyes are stuck.
Fortunately, we need methane, it's near the top of the water. Anybody in here not get who's a Anybody else not who's a
Oh, never mind. This is cool.
Okay, good.
I thought.
All right, let's go ahead and work this one. So I'm going to scoot down to where methane is still barely on the screen, and then I'm going to just remind us what the reaction is. So with methane, it reacts with oxygen, right? They're both gases, to make water plus CO2. I need 2 of these and 2 of those, yes? Yes. Okay, so to get the enthalpy, standard enthalpy for this reaction, I'm going to use the, not enthalpy, the standard free energy of reaction, I'm going to use the free energies of formation. And so for methane, it's right here, that, right? Well, that's a reactant though. It's got to be products minus reactants. Let's not start with methane then. Let's start with the water. So water, it's going to be 2 times, where's my water number? There. Negative 228.6 plus, I've got carbon dioxide. Carbon dioxide's right here. And there's 1 of those, so 1 times negative 394.4 minus, inside here I'm going to have the methane. So there's 1 methane, right? So 1 times negative 50.5 plus, and then I've got oxygen, which we added here, right? And there's going to be 2 oxygens times 0. So I can put all those into my calculator, and I'm going to get 801. There's another digit there. What's the other digit? 0.1. Okay. And our units up here were, we weren't adding their units, but these are our units. Kilojoules per mole. Questions on that process? So that works for all of those processes that are state functions. You can, if anything it's a state function, you can do that sort of thing. You can add reactions together. And that's what we're doing there with this products minus reactants. We're actually just adding all those reactions together. Okay. Before I go on, any questions? All right. Then I want to talk about how free energy is related to equilibrium. All right, when we think about equilibrium, you know, we could think about having a graph here where we have free energy on the y-axis. And on the x-axis, let's say our reaction goes A plus B goes to C plus D again. And let's say we have A plus B right here and C plus D over here. And this is all and all. Make that a D. Okay, so we're either all reactants here or all products here, and you could think about the free energy of the system. So things in nature, what they do is they move from higher energy states to lower energy states. And so you could imagine, let's imagine the free energy looks like this curve. Yeah, we'll do that. It doesn't have to get up to the same point. But what we've got here is a curve here. Here's the lowest point of the curve, and that is where equilibrium is. Okay? So our lowest point, so essentially if we start with all reactants, they're going to react and become, we're going to make products until we get to here. And at this point, the rate of making products will be equal to the rate of making reactants, and we will get no net change. So at equilibrium, it isn't that you have no change, it's just for every reactant you make, you're making a product. Does that make sense? Okay. Another thing I want to point out here is I have equilibrium here. My equilibrium is my equilibrium where I'm midway between where I've got equal everything. Equilibrium does not mean I have equal reactants and products. Okay. And so I've carefully drawn that to make sure.
Didn't you talk about delta G being 0 equilibrium?
Yeah, we will talk about that. Okay, so delta G is 0, but this is all a relative sort of thing.
Oh, so free energy isn't delta G, it's just free energy of one and free energy of the other.
Well, free energy can be positive or negative. So this is just the lowest
Okay.
point for free energy. And when we talk about free energy being positive or negative, we're talking about changes. Okay. If we were going to have free energy be 0, it would have to be at, it's probably a perfect crystal at absolute 0.
Gotcha. Okay.
Okay. Questions? So the free energy at 0 we talk about is the change being 0. Okay. And so what that means, that's a good point though. We're at equilibrium here. Okay. We did our correction right here. Oh no, we haven't done our correction. We did our correction up here, right? For our free energy. Our delta G is equal to 0 at equilibrium. Okay. And our delta G over here, let me draw it. Delta G is greater than 0 over here. We're favoring our product. Well, no, delta G is actually, nope. Delta G is actually less than 0 over here because we're going to go to the right. And delta G, these aren't standard delta G's, is greater than 0 over here because we're going to go to the left. Right? We think about spontaneity being, it's spontaneous in this direction, right? If we're up here, or right here, we're going to be spontaneous in this direction. If we're right here, we're going to move this direction, non-spontaneous. We think about non-spontaneous, meaning the reaction goes that way. Does that make sense? Okay, so given that, go ahead and try to answer this one. Okay? Dakota, could you see the text? Yeah. Okay. Go ahead and try to answer those 4. I'll give you a couple minutes for it. All right, why don't we go ahead and work through these? So does this reaction favor C or D? Equilibrium is right here. So what are we favoring? D, because equilibrium is closer to D. If we're closer to products, we make more products at equilibrium, is K greater than 1 or less than 1? Greater than 1. Remember, K is going to be products over reactants. And so if we have more products at equilibrium, K is greater than 1. Okay. Is the delta G for this reaction, the standard delta G for this reaction, positive or negative? Negative, because we're favoring our products, right? We would say this one's spontaneous. Okay, and if the reaction contains equal numbers of or equal amounts of C and D, so right here, which way do we go, right or left? Right, we're gonna move to lower energy, which is right here. Questions on that?
Why is G negative?
Why is G negative?
Yeah, there's more.
Right, good question. So why is delta G negative? Negative, so if we go this way, right, if the reaction's gonna go that way, or spontaneous, so it's spontaneous if it's going that direction, and that means that delta G is less than 0, or it's negative. Right, a spontaneous reaction favors the products. Alessandra?
I don't know if I copied something down wrong, but could you maybe go to the graph you drew above this one where you had the change of the G from 0?
Did I write it wrong?
I don't know, maybe I wrote it wrong.
Well, let's check it. Let's correct it if I did.
So if the changing the free gas is positive on the right side of the graph, why would it be negative in the example of the C?
Are you talking about these?
Yeah.
Okay, these are actual delta G's, not standard free energies. They're the free energies. So when I'm here, my free energy change, I should say, is going to be negative moving this direction.
Okay.
What we're saying is when we're using that free energy change to say based on where we are, we're saying free energy is how far away from equilibrium and to which side. And when delta G is negative, it tells you you need to go to the right. And when delta G is positive, it tells you you need to go to the left. But these are, notice they don't have the little circles. So they are different, but they are going the same directions as well. Good question. Other questions? Okay. Realize a lot of this stuff is a little confusing. All right, so we're going to actually go ahead and finish off for today by doing a calculation problem. So what I would like with that, so actually I haven't defined the equation. Let's go ahead and define the equation, and then we'll do a calculation problem. So we've got this equation, right? It says, hey, our actual free energy change is equal to our standard free energy change plus RT, natural logarithm of Q, right? Okay. Well, if we're at equilibrium is at, we can use this to calculate what equilibrium is. So if our delta G is 0, what condition is that? Equilibrium when our delta G is 0, right? And when our delta G is 0, QC can be any set of ratios, right? We'll do our A plus B goes to C plus D, okay? So that's going to be C over D over A times B, like that. That's the same thing as our equilibrium constant, right? Like that. Okay? They look the same. How are they different? This set of ratios here, this is only at equilibrium. So this set of ratios, this is only valid only at equilibrium, whereas these ratios can be anything. Does that make sense? So if we think about our reaction path right here, KC is equal to QC, okay? But everywhere else, they're not, everywhere else, I mean, this is KC right here. But QC can be anything on this line. So QC can be up here or here. Can you even see that yellow? Yeah, you can. Okay, does that make sense? So what that means is when we're at equilibrium, when delta G is 0, we can substitute in for Q with the equilibrium constant. Good to see there. Okay, and so, I'm sorry, I'm running a little short on time here, so what I'm gonna do is, I can subtract this from both sides, right? I'll write it out. Negative RT ln of Kc, negative RT of ln of Kc. I'm gonna pass out your exams while you work the problem. And so this is going to give me negative RT logarithm of Kc is equal to delta G, the standard for energy. And then I'm just going to flip these because usually it's written like this in books. Okay? And so now I have a relationship of free energy, standard free energy change to what my equilibrium constant is going to be. And this is interesting, is useful. You have to do these sorts of, I have to do these sorts of conversions all the time in my research, especially because I work with physicists who do biology, and they think about everything in terms of delta G. And I'm a biochemist, and I think about everything in terms of equilibrium constants. But they're completely interconvertible. So I want to remind you that this is 8.314 joules per mole times Kelvin. And I would like you to try to work this problem there. So what I want you to do is calculate Kc for only this one. I'm going to cross out the one below it because it actually had different moles of gases, and so Kc, you have to do that conversion from Kc to Kp. Yes. What's the temperature? Thank you. 298. Okay. So what I put up on the board is you're going to calculate Kc for that, and I left this, I've got it stretched out funny, I'm not showing you the top of the problem, because this is the equation you use to do it. And we'll start passing out your tests. Maybe wait to look at it until you're done working the problem. It just is Kc is what you're solving. So for Kc, you're going to have to do what with your calculator? Solve for it. You're going to have to raise both sides to equal. Okay, let me go ahead and work it real quick, and then if you don't have your test back yet, hang out so I can hand it back to you. And do check that I had somebody last time that was having problems with the E key on their calculator. So if you're having problems, please come up and see me. I'm gonna have you guys help me out and remind me, well, actually, I'll just look at it. What was so I need to use this equation, and what I really just need from this thing is it 27.2 kilojoules per mole. So this is 27.2 kilojoules per mole, right? Okay. Whoops, I actually didn't put it into joules, so in my head, I'm gonna convert my ideal gas constant into kilojoules. All right, so that's gonna be negative 0.008314 kilojoules per mole. Ooh. No, it's not. Oh, maybe my pen is battery? Anyway, joules per mole Kelvin times the temperature, which was 298 from the problem up above, times the natural logarithm, and Kc is what we're solving for. All right, I don't want to hold you extra here, so I'm going to divide both sides into this, all right, to get it all on the same side. So that's 27.2 divided by 0.008314 divided by 298, and I've got 10.9 or whatever. Okay, negative 10.9. And then I'm going to raise that to the E. And what I get out of that is my answer for Kc. And if you don't get this, maybe you want to ask me about it. We can go over it. 1, 2, 3, 4, 5. Okay, so let's just do it. 1.7 times 10 to the negative 5th. All right, and there are no units on equilibrium constants until you get to biochem. Questions? Okay, let me hand back the rest of the test. If you haven't gotten your test, please hang out. If you have gotten your test, don't worry about it. The answer key for these are posted. You're also welcome to, please look at it, but you're also welcome to just come and talk to me.
Thank you.
Have a good one.
Start with mine.